Hello and welcome to a new video in a course on calculus. In the previous videos, we discussed the definition of sequences and we discussed the definition of limits, and we gave some tools for computing limits of sequences. So in this video and in the coming videos, we'll be working on a new chapter where we will discuss infinite series. So I remind you real quick, a sequence is a list of numbers where order matters and repetition is allowed, okay? So this is what a sequence is. Now, series, on the other hand, is roughly speaking a way of adding infinitely many terms or infinitely many numbers, right? So it's important to make a distinction here. So a sequence is a list, right? It's a list. The series, a series is a sum, right? This distinction is important for you. So we're gonna add, so say we have a sequence of numbers an, we're gonna add all its terms in this order, say, right? So this is what a series is. So in simple terms, a series is an infinite sum of numbers. Now, whether or not this sum makes sense, i.e. whether or not this sum converges, is a different question that we're gonna tackle probably in the coming video. However, the purpose of this video is to give some examples of series and to cover the basic properties of series, like how to add two series, how to multiply two series, how to re-index series, and some of the important examples of series. So an important terminology here that I want to introduce is the term partial sum. So say you have a series, the sum of from n equals 1 to infinity of an, a partial sum of this series is denoted by s sub n, where you sum n terms from that sequence. So you sum n terms of the AIs, right? So instead of summing the infinite terms, you stop at the nth term. So this is what's so-called a partial sum, or in other words, or more precisely, it's called the nth partial sum. So it's called the nth partial sum because we're summing n terms. Now, the question of convergence of series is going to be discussed in the coming video. However, just in case I had to use the term convergent series, let me just define to you what it means for the series to be convergent, right? So you have a series, the sum of an from n equals 1 to infinity, right? So for this series, we said that we have the concept of what's so-called an nth partial sum, right? So this is what we have. And the nth partial sum is defined as the sum of a sub I from I equals 1 to n. So this is the nth partial sum. Now, a series of this form is said to be convergent. So this is convergent if the limit of Sn as n tends to infinity exists, right? So if this limit exists, then we say that the series converges, right? So this is more of a definition, I would say. So a series of this form converges to a number s if the limit of the partial sum is equal to s, right? And we say a series diverges to infinity if the limit is equal to infinity, or a series diverges if the limit does not exist, right? So we will be looking at properties. We will be looking at this concept in the next video, but for now, let us discuss some examples and properties. So the first example I want to go over is what's so-called a harmonic series. So this term, please, you have to remember this, because these are concepts and terms that will be appearing over and over again, and these are some of the most important examples of series you will encounter. So a harmonic series is the series of the form the summation of 1 over n from n equals 1 to infinity, right? So I want to point out here that the sequence an that we're working with is 1 over n, and what we're doing is that we're summing all the terms of that sequence. So we're gonna sum 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 up to infinity. So we're gonna be doing this forever, right? So this is a series. What's the nth partial sum of that series? Well, here's the nth partial sum, right? And as you will see in the coming video, this is a natural example, or in other words, this is something that you should immediately think of when you're asked to give an example of an infinite series that is divergent. So we will see in the coming video when we discuss the integral test or other tests that why this series is actually divergent, right? So this is an example of series. Keep this in mind. So the next example that we want to go over is what's so-called geometric series. So this is yet another very important example of series to keep in mind. So series that take the form the sum of r to the n as n goes from 0 to infinity. So let me just give you an example. See, here's an example. Maybe here it is. No need to write it. And as a quick example here, the sum from n equals 0 to infinity of 1 over 2 to the n, if you take r to be 1 over 2 and if you take a to be 1, then the series that we have is the sum of 1 over 2 to the n as n ranges from n equals 0 to infinity. Now, one very interesting property about this series is that you can write the answer of it, like you can write the sum of all of its term as a little answer. Like you can find the limit as in a compact form. Like the limit has a compact form, because remember this is equal to the limit as n tends to infinity, or maybe let me use big N here to avoid confusion, of the sum from n equals 0 to n of a r to the n. So this is the nth partial sum, right? Let me just put here quote unquote because this might not converge. So if r is less than 1, we have a compact form for the series. Like we can express this limit in this form, right? We have this compact form, and we're gonna prove this now. We're gonna show this now, right? And the reason this is important is that whenever you see such an example of a series or such a form of a series, you will immediately know what the answer is. You will immediately know, just as for here, you like if you plug here in this formula, if you plug a equals 1 and r equals half, these are coming from here, like if you plug these in this formula, you will have 1 over 1 minus 1 over 2. And if you take a common denominator here and do the arithmetic, it's going to be 1 over 2. And then this is 2, right? So you can get the answer, like surprisingly, like the sum of 1 over 2 to the power 0 plus 1 over 2 plus 1 over 2 squared plus 1 over 2 cubed. If you do this up till infinity, the answer is 2. Like, surprisingly enough, the answer is a little number and it is 2, right? So let us prove why this formula holds. And you might see here that I'm saying if r is bigger than or equal to 1, the series diverges. We're gonna see this. We're gonna prove this. So here's a quick way of showing why the sum from n equals 0 to infinity of a r to the n is equal to a over 1 minus r for r in absolute value strictly less than 1, right? So again, this is a limit, right? It's important to keep this in mind. What is a series? It's a limit, right? It's a limit of what? It's a limit of the partial sums. Like this is the very definition of what a series is. Sure, it is an infinite sum of numbers, but how would you make sense of this term infinite sum, right? So it's a limit. It's a limit of a partial sum. So what's the partial sum here? What's s sub n? What's the nth partial sum? It's the sum from n equals 0 to big N of a r to the n, right? So we sum n terms, we sum big N terms, right? So so we need to check if the limit of this partial sum exists, and if it does, then this series exists, and in other words, is convergent, and its limit is gonna be the or its value is gonna be the limit of this thing. So let us consider what's the limit as n tends to infinity of Sn. So let's ask the question if this exists or not, and if it does, what's the answer? So if you look at Sn, it can be rewritten as a times r to the 0, but r to the let me just mention here that we're not taking r to be 0, right? Because if r is 0, then this sum is just 0, right? We're not interested in that. So what's this partial sum? It's a times r to the power 0, which is a, plus a times r, plus a times r squared, plus so on up to a times r to the power n. Now let's do this trick of multiplying this by r, right? What happens if we multiply this sum by r? Well, it's going to be ar plus ar squared plus ar cubed plus so on plus ar to the n plus 1, right? So let us now do another trick, which is we're going to subtract these two. Let's subtract these. If we subtract these two, what do we get? We get Sn minus r Sn is equal to. And notice some cancellations will happen here. So let us do this. So this term will cancel with this term because we're subtracting the two. This term will cancel with this term. And the term that's going to come here will cancel with this. And so on and so on. Let me just write an extra term here, perhaps just to make the idea clear. So here there is another term, which is ar to the n, right? And this term is going to cancel with this term, and what we'll be left with is this a, right? It's going to be left, and over here, since we're taking a minus of this thing, it's going to be a minus here, so it's going to be minus a r to the n plus 1, right? So if we rewrite this left hand side, if we rewrite it as, if we take s to the n in common, and we will be having 1 minus r in here, and this is gonna be a times 1 minus, if we take a common, to the 1 minus r to the n plus 1. This is what we have, right? So here comes the importance of this assumption. The importance of this assumption, it's very important. So and there's another place where it's important. Now, since r in absolute value is less than 1, then 1 minus r is not 0. I hope this is clear, right? Since r is a number that is strictly less than 1, 1 minus r cannot be 0, right? Now, we can divide by 1 minus r, and what we have is that Sn is equal to a times 1 minus r to the n plus 1 over 1 minus r. We just divided by 1 minus r, right? And now we're gonna ask, does the limit of Sn exist as n tends to infinity? What's the limit of Sn? Well, so here comes the importance of r less than 1. This is also another place where this property is important. So if you look at this, if we take the limit here, what are we gonna get? So it's gonna be the limit as n tends to infinity of a times 1 minus r to the n plus 1. And I guess now you guys are comfortable doing limits. This is what? Well, the only place where n shows up is here, right? And if we just quote unquote start by replacing n equals infinity, what do we get? We get so for the rest of the terms will be the same, and over here we will have r to the infinity. But since r is less than 1, r to the infinity is 0, right? Since r is strictly less than 1, r to the infinity is 0, quote unquote r to the infinity is 0, then this limit is gonna be a times 1 minus 0 over 1 minus r, but this is the same as a over 1 minus r, and this is exactly what we were looking for, right? This limit exists and it is equal to this number, and thus this series exists, this infinite sum of numbers exists, and it is equal to that number. And I know that you guys are comfortable with limits now, but it might be that it's not clear to you why the limit, or why quote unquote r to the infinity is 0 when r is less than 1. So let me state this limit and prove it real quick, because it might not be clear to some people. So why is the limit of r to the n as n tends to infinity equal to 0 if r in absolute value is strictly less than 1, not equal to 0? So, well, if it's 0, it's evident. So why is that the case? Well, let us prove that the limit of the absolute value of Rn as n tends to infinity is equal to 0. Because if we can prove that, then certainly the limit of this thing will be 0, right? So why is the limit of the absolute value of r to the n equal to 0? Well, if you call this sequence an, then an, let's say an plus 1 is equal to r to an absolute value to the n plus 1, and this is equal to r in absolute value times an. And now let's take limits both sides. What we get is that let me just mention here something. Since this is less than 1, then this is strictly less than 1 times an, which means this is equal to an, which means that this sequence an is decreasing, right? It's decreasing, but r to the n, which is an, is bounded below by 0. So this is bounded below by 0, right? So proving that this limit is actually a problem on its own, but actually it's an interesting thing to do. So let us do it, and I advise you again to keep track of the tricks appearing in these proofs, because these are very important. So first of all, we're gonna note that the limit exists, right? So the first step in proving a limit is something, is a number, is perhaps proving that, or at least giving yourself some confidence that the limit does exist, right? So our limit or our sequence is bounded below by 0, and it's decreasing. So since it's decreasing and bounded below, then by the monotone sequence theorem that we covered in the previous video, we have that an is convergent. So this is a little bit of digression, but I have to cover this, so this is a digression. So the sequence is convergent, which means we can call its limit L, the limit of n of a n as n tends to infinity. This exists. Alright, and since this limit exists, we now go back and note that since an is equals to r times an, it's coming from this property here, this equality. If we send n to infinity, both sides, what do we get? We get a limit of an as n tends to infinity, which is L, right? So here, sending n to infinity, or taking limits, both sides. And on the other hand, we're going to have here r times the same L, because it's the same sequence, we're taking the limit of it as n tends to infinity, right? So this is the same, or this means that if we take L, if we bring this to the other side, and if we take L common, we're gonna have L into 1 minus the absolute value of R is equal to 0, right? But R is strictly less than 1, right? R is strictly less than 1, which means that this is never 0. But if this is never 0, this forces L itself to be 0, right? So this means that L is 0. Now, what is L? Well, remember, L is the limit of an. And who is an? An is this thing. So we just proved that the limit of this thing is equal to 0. And this is all we needed to do, right? So this is a bit of digression, just for you to know that actually it's an important limit to go over. And I advise you to study the tricks behind this limit, because they are very important actually. So back to our discussion on series. So let me just wrap up our discussion here. So what we proved is that geometric series that take the form the sum from n equals 0 to infinity of a times r to the n, they actually converge for r strictly less than 1. And not only that, but also we can write them in this compact form. Okay? And we're gonna talk about divergence later of these of this series. And perhaps we can mention that divergence is also evident when r is bigger than or equal to 1, because remember, I maybe I should mention this real quick, because it's an important thing to notice here. So maybe it's important to discuss why this series is divergent for r strictly bigger than or equal to 1. So let us do that, I guess, since we already discussed this in detail. So let us do that. Why is it divergent? Remember, what it means for the series to converge or diverge depends on what the partial sum does, right? Because a series is eventually just the limit of a partial sum. So if the limit of the partial sum exists, then we say that the series is convergent, and this is what we did to prove this thing. And if the limit of the series diverge, then the series itself diverges, right? So let us see why this geometric series diverges if r is bigger than or equal to 1. Let us prove this. This is important, actually. Let's show this. So here's a problem. Show that the sum a r to the n from n equals 0 to infinity of a r to the n diverges for r bigger than or equal to 1. So let us show this. So solution. So the solution here is an easy thing now that we've discussed what the partial sum is. But let us observe that for r equals 1, this is clear, because the sum is now 1 to the n, just as we discussed, from n equals 0 to infinity, which is equal to the sum of a times 1, because that's 1, to infinity, which is equal to so there's a times here, a times the sum of 1 from n equals 0 to infinity, and you're summing, we're assuming a is not 0, of course. We're summing here infinitely many ones, so the sum is actually infinity. Now, for r in absolute value strictly bigger than 1, why is this the case? Why is it the case that this sum is divergent? Let us just recall real quick that we've shown that Sn can be written as such. Okay? So this is an important formula for you to remember, or at least the trick of showing it, because you can rederive it if you forgot it. But it's important to remember it. It's actually very important formula. So Sn, the nth partial sum of the Sn, the nth partial sum of the geometric series, is actually equal to a times 1 minus r to the n plus 1 over 1 minus r. So let me just copy this here. So Sn is equal to a times 1 minus r to the n plus 1 over 1 minus r. So let me just mention here, why are we looking at the partial sum? Well, because the series itself, it exists or it doesn't exist. Whether it exists or it doesn't exist depends on whether the limit of the partial sum exists or doesn't exist, right? So when r is less than 1, we managed to show that the limit exists and it's equal to something, it's equal to a formula, and we said that thus the series is convergent and it's equal to that number. Now, for r strictly bigger than 1, we're going to also look at the partial sum, and we're claiming that the series diverges, so we're going to show that the limit of this does not exist, or in other words, equal to infinity, okay? So if you take limits of this, what's the limit as n tends to infinity of Sn? Well, this is equal to a, this is equal to the limit of this thing, of a times 1 minus r to the n plus 1, over 1 minus r. So the only term that depends on n here is this thing, right? And it's so let us understand what's the limit of r to the n plus 1 as n tends to infinity. So I claim that this limit is infinity, right? So this limit is infinity. In fact, if r is negative, the limit does not exist, right? So if r is negative, because remember we're talking about r strictly bigger than 1, so r can be positive or negative in absolute value. So if r is negative, clearly limit does not exist. So the limit of this alternating, it's going to be an alternating sequence. The limit does not exist. Now if r is positive and it's strictly bigger than 1, then it's going to be, the limit is going to be infinity. And I'm going to leave it as an exercise for you, but as a small hint for you, well, this is going to be an increasing sequence. So an equals to r to the, let me just use big N, an equals to r to the n plus 1, right? This is increasing. We're assuming here r is bigger than 1. So this is increasing and unbounded. And an increasing sequence that is unbounded, it's divergent by the monotone theorem. Alright, so this is what we have. So the limit of this, in either case, it's either infinity or it doesn't exist, right? So in either case, the limit does not exist, and thus the series is divergent for r strict bigger than or equal to 1, right? So just keep in mind, geometric series, it's an important series. It makes a lot of sense when r is strictly less than 1, and it has a nice formula that you should remember. And when r is bigger than or equal to 1, the series is divergent, okay? So as an exercise for you, just as I showed you why the limit because just I plugged the a and r here. I showed you why the limit of this 1 over 2 to the n is equal to 2 as an exercise for you. Show or find the sum of 1 over 3 to the n as from n equals 0 to infinity. Maybe I should tell you show, because this is just 3 over 2 actually. So I'm gonna just leave it as an exercise for you to plug the a and the r of this series in this formula and verify that it should be this number, right? So this is what's so-called geometric series. I wanted to discuss two more concepts before we wrap up this video. These are easier concepts to go over, and these are how do we sum two series, right? So here's the thing: when you want to sum two series, you have to be summing numbers, right? They have to be actual numbers. They have to make sense, right? You can't just tell me I'm summing. You can't just tell me I'm summing infinity and something that doesn't exist, right? Because remember, at the end of the day, I'm trying to repeat this over and over again, because I can't stress how important is this. A series is a limit, right? If the limit does not exist, you can't tell me I'm adding two limits if the limits do not exist, right? They have to exist in the first place for you to be able to add them, right? So this, say you have a limit here, you have a series here and a series here, right? These are limits. So if in the case that they are convergent, in the case that the limit of their partial sums is convergent, then their sums are numbers, their sums make sense, then we can sum them, we can take differences, then we can sum them and we can take differences of these, and we're defining the sum of an plus the sum of bn to be like you sum them element wise, and the sum of an minus the sum of bn, you also sum them element wise, right? I wanted to give this example, but since we haven't covered why these series are convergent, I'm gonna give you a different example here. I'm gonna give you here another example of how to sum series. So remember, the sum of 1 over 2 to the n, as n goes from 0 to infinity, we showed that this is 2 because this is a geometric series, right? And the sum of 1 over 3 to the n, as n ranges from 0 to infinity, I gave you this as an exercise. I gave you this as an exercise to show that it's equal to 3 over 2, and thus what this is saying, what this thing is saying, is that if you sum 1 over 2 plus 1 over 3 to the n, right, from n equals 0 to infinity, if you take this sum as one sum, this is the same as summing the first sum, 1 over 2 to the n, plus the sum of 1 over 3 to the n equals 0 to infinity, and this is the same as taking so this is 2 and this is 3 over 2, and this is the number that we get. So this is what? This is 7 over 2, right? So it's important here to see that I used the fact that these two are convergent series. So this is a 3, excuse me. These are convergent series, and thus we can sum them by distributing the sums, right? So we're gonna be talking about this more later when we discuss why these series are convergent by these are called P series. We'll be talking about these in the next video. So this is how you sum series. How do you sum two series that are convergent? You sum them element wise. Okay, this is important for you to keep in mind. Other than that, I just needed to cover how to re-index series, because this concept is very important. It's gonna show up over and over again. So I'm gonna before I tell you what the general rule is, perhaps I should tell you, maybe we should take an example here, a simpler example. So let's take an example. So let's take the sum of 1 over 2 to the n as n goes from 0 to infinity. Okay, so this, we know that this is equal to 2, right? Now say you have a problem, or say you got a question. Find the sum from n equals 1 to infinity of 1 over 2 to the n, of 1 over 2 to the n. Well, before you just rush and say this is equal to 2, remember there is a term that is missing here. In fact, there's a term that is equal to 1, because it's 1 over 2 to the power 0, and that 1 is missing from here. We're not adding this here, right? So there is a missing term in this series. So here comes the importance of re-indexing a series, right? So how do we re-index a series? So the general rule is that, so if you're starting at R, right? If you have a sequence here, AK, and you're starting it at R and you want to start it at 0, okay, what you do is that you add R to the index and then you start it at 0. Okay, so let me just give you the example and then I'm going to justify what's happening. So this is the same as, we want to start it from 0, right, to infinity, and this is 1 over 2. Okay, it's gonna keep the same index. However, since we had 1 here, we're gonna add 1 here. Okay, so what we do is that to re-index this, to start from 0, we have to add R. We have to add R to the indexing, right? And in this case, right, what is that? So this is 1 over 2 to the n times 1 over 2, because remember, when we multiply two numbers, a to the m times a to the n, we add the exponents, right? It's a to the m plus n, right? So this is gonna be 1 over 2, a half can be taken out, times the sum from n equals 0 to infinity of 1 over 2 to the n, right? And we know that this is 2 from here, excuse me, we know that this is 2, and thus the answer is 1 over 2 times 2, which is 1, which is what we expected, because we only removed the term corresponding to n equals 0, and the term corresponding to n equals 0 is 1 over 2 to the 0, which is 1. So we removed 1 from the answer, so this is why we got 1, right? So perhaps I'm also using something that I should perhaps mention here, that the reason this is true is that perhaps I didn't mention this. So the reason this is true is that a series is just a limit, and thus since the limit respects the arithmetic operations, so does the series, right? So does the convergent series, and particularly if we multiply this by a number r, so if we have an from n equals whatever 1 to infinity of this sequence, we can take the r outside, because of course if the limit is convergent, we can take the r outside, because just this is just a limit, right? And the limit respects the operation. Remember, when you have a limit, you can pull the constants outside the limit, and I mean, that's it, right? This thing I've been using, that you can pull a constant outside the the infinite series. Anyways, anyways, let's see here. So yeah, this is what we had, right? So this is one important example of why we need re-indexing here, right? So so sometimes this constant is annoying to you and you want to get rid of it, and the way you get rid of it is that you start from it, and sometimes you want to start from zero and you go back. So this is the formula, right? The formula says if you have a sum from n equals 0 to infinity of a sub n plus r, you can rewrite this as the sum from k equals r to infinity of ak. Now, how do you remember this? Because this is important, right? It's not clear how one can remember that, right? So what we're really doing is what's so-called a change of variable. So we're changing the variable that we're using, right? So it's annoying for you if this is annoying for you, right? And you want to start from k rather than starting from like you want like you want the indexing to be by one term and not by two terms, like not by a sum of terms, right? By a sum of numbers. So what you're gonna do is that you're gonna take a change of variable k equals to n plus r, right? If you do that, then this sum, like the a here is gonna be indexed by k. However, you have to change the boundary of the sum, right? If n is 0, when n is 0, k is equal to 0 plus r is equal to r. And this is why we're starting at r here, right? I'm going to give you an explicit example to see this. When n is infinity from here, well, k is infinity plus r, which is infinity. And this is why we're putting infinity here. So I hope the idea of reindexing is clear. So it's all like a change of variable that we have to do, right? So you can memorize this as is, and you can remember that what we're doing is a change of variable, right? So let's take an explicit example of reindexing, because this might be helpful to see an example. Okay. So look at this series, and say, since it's starting at 2, it's kind of annoying. Say we want to start it at 1, right? What do we do? What do we do to make this start at 1? Okay, so let's see here. So we want to like the variable here is n, right? Or the index here, the indexing that we're using is by n. So we want to introduce a new indexing that starts at 1. So let's call that indexing k, right? So what can I take k so that when n is 2, k is 1? Well, one obvious way of doing that is to take n minus 1. You see, since n is starting at 2, when you plug, like when n is 2, what you do is that you have k is equal to 2 minus 1, which is equal to 1. So k starts at 1. And when n is infinity, you have k is equal to infinity minus 1, which is equal to infinity, which is why we have this. Now, very important here, when you change the indexing variable, for example, here we changed it to k, you have to change it back in the summand. So this is called the summand, the thing we're summing, right? You have to change it back because you no longer have n here as an indexing, so you have to change it inside the thing you're summing, because it doesn't make sense to keep an n there, because what is n here? There's no n if we change the indexing of the summand, right? So how do we change the thing inside? Well, we have that so from here we have that n is equal to if we take the 1 to the other side, we have n is equal to k plus 1. So if we substitute n equals k plus 1 in here, so if we put here k plus 1, we get this. And if we put here, instead of this k plus 1, we have k plus 1 minus 1, the plus 1 and the minus 1 will cancel, and we'll be left with k. Okay, so it's all about a change of variable. You wish to start at 1, you introduce this trick, you subtract 1 from n. Okay, so I hope that this is clear. So one way to remember this is to remember this formula and adapt it whenever you need, and the other way is to just remember that it's all a change of variable, that is n equals k minus r, where r is the number you're starting at, and you wish to go back to 0, right? So this is all I wanted to mention in this video, and in next coming videos we'll be reiterating over these concepts, and we'll be covering examples of, and we'll be covering tests that allows you to prove or disprove convergence of series.